Okay, so I'm big on like note cards, just an analytic, or sorry, not analytic, oh my god, I'm like too deep into computational methods. Analog, that's the word I'm looking for. Just a nice analog, get your thoughts onto paper. So I'll hand these out. It's not, I'm not you can turn them back in if you want, but it's more just to get you writing something. So first thing, we're going to use one side of note cards, write down like topics or ideas or maybe skills that we're working on in module 1, and we'll flip it over, write down a problem, like either a diagram or a problem statement, and we'll figure out like what we should have on quiz 1.
What are the odds that I get it? That was the whole social it's super simple. First guess, if I was like, I have access to several $1,000 on technology right now. So I pulled it straight to the water all the way up. So I was like, shit, if there's like a silent alarm goes off, dude pulls into the truck, goes straight to the end of the station building as I'm walking out there. I stare at him and I smile. He doesn't break my eyes. So I wait, I go back and talk to him. Where did you I saw the alarm. I was like, what are you talking about? He was a guy that I just thought it was weird that it's all oh, yeah. I wouldn't be surprised. That's not too bad. But I don't know what's a good I usually write more than I was
but they tell you the font size is
blew up or maybe it's that's funny. I bet you they're gonna update it since we're post-COVID. Okay, I did change part of it. Maybe they say that makes sense. Oh, yes, just put yourself in one of those humongous ventilation rooms. I was debating asking And they were like, so you just have XMT. Yeah. And I just stayed and I forgot it was another type of and I was like, where is different species. Oh fuck. Then I saw the next slide where the slide was on the same like it just stayed down to everyone else just branched out. They're like, remember the Neanderthals? I was like, yeah. Some of the ancestors made in the past other species like state within the learn how can you apply it. She's gonna put a smiley face on it. I have a question. Are we supposed to? I am very chill. Well, no, so I just want to ask because you want us to like use a website or function to make a bot.
Yeah, I like Python personally. I know we didn't. Hang on to it. Yeah. What do you have?
I didn't have a pen, but I do.
Do you need a pen?
I need one.
All right. I think it helps to write down, but yeah, go for it. Engineer and meeting without a pencil is like a soldier without a sword. Gotta have a pencil. So big one that I saw a few times, free body diagrams. What was that? What is that giving us? Like we talked a lot about free body diagrams. What is that telling us? All right, so is a free body diagram telling you the motion of the object? Like how to describe motion? No? What does the free body diagram tell you? Forces acting on it? Yeah. So I think one of the first questions I kind of asked was like, what's the difference between kinematics and kinetics? Does anyone remember what the kinetics were versus kinematics? Yeah. One is force vectors, the other one, what's the other one? Yeah, so kinematics is strictly like how do you describe motion? Like it's almost like an observation of like what is this motion? What's happening here? Kinetics, that's our free body diagram. What are the things that can cause motion? And we kind of the way all dynamics problems work is like almost like a Sudoku puzzle. You put things together, there's missing things here and there, then you start solving for the missing pieces. Or crossword puzzle, or I don't know, any kind of puzzle where you just like, you know kind of what stuff should be. So this is like our kinetics. And then what else did people write as I was talking about that? I forgot. Oh, vectors. What were we using vectors for? What was a vector? Direction? Direction. It's giving us like some guiding light. It's our North Star is the vector. We follow the vector always. We used a lot of vectors. So let's chip away. What's something that we talked about that is not a vector? Was there anything that was not a vector? Speed. Speed is not a vector. What is speed? It's a magnitude of a vector. Yeah. Mass, not a vector. Acceleration. Acceleration should be vector, right? It should have like some kind of direction and then some magnitude. But yeah, if you think about like magnitude of acceleration, like how many G's was it? Like how fast was I accelerating? A lot of times that's considered as just what is the magnitude, and that doesn't necessarily have a direction. So vectors, that's our position. Whoop. It's our velocity. It's our acceleration. It's not mass. It's tough to have a to have a direction with your mass. Of like I'm 190 pounds standing this way, but if I turn sideways, I'm only 30 pounds. It'd be kind of weird, right? Mass is not jerk and snap. Oh yeah, take more derivative. So yeah, once you can do like the jerk. Jerk is the acceleration, the derivative of acceleration. Snap, derivative of the jerk, which is derivative of the derivative of acceleration. Thanks. And then because acceleration's a vector, that's kind of the magic of Newton's second law. I mean, it's ingrained in our memories of like F will always be ma, but the real magic there is that because F is ma, all F's have to be a vector. You can't, which kind of makes sense, but force is really like an odd concept. Because force is really a measurement of like how much you can move something, how well you can move something. But we don't have to get into unless you want to get into like the philosophy and the measurement science of what is a force. Do we even know what this universe is? Or what is mass? Nobody really knows what mass is. We have a general sense, we have some quantum mechanics definitions of it, but it's pretty, as you get down to it, it's kind of circular reasoning. What else did we cover for Module 1? Free body diagrams, vectors. Think we got it? Yeah. Directions of motion, okay. So I guess I'm gonna kind of paraphrase this, and you can correct me if you're like, that's not what I'm talking about. But we were kind of looking at like, okay, what are the causes of motion? What is the predicted motion based on the things that we see causing motion? That's kind of how I'm seeing that. Of like we saw what constraints we had, we were looking at what forces there were, solve for where's this thing gonna go, make a prediction. And that's And really that's what the kinematic equations are. They're kinematic because it's a solution for, if you have constant force, this is the solution for acceleration under constant force. I like that. Oh yeah, last thing I did see a couple of times was creating, I'm gonna say, equations of motion, ODEs, and then solving those equations of motion. That was like the last thing that we worked on Friday, right before the weekend. It's like, how do we, once we know this is our differential equation, where do we go from there? This is not a class on differential equations, so really there's just those three types. We either have constant forces, kind of exponential decay sort of forces, or oscillating. And then when you get into like vibrations and other control theory stuff, then you can look at like all the coupled mechanics of all that. That's where it gets really fun, all the cool stuff. Or go into like control theory where you start putting feedback loops on top of things. And then it's real. Then you get into like the real cool like math about stuff. But first we got to set it all up, right? We need a good prediction for motion. Then we can try to control motion. Did I miss anything? I mean, you have things on your note cards. Does this match exact? This is like, you're like, wow, it's like looking in a mirror. That's also in a mirror because I can read it in both sides. It's not the reverse of what I wrote. Good? All right, so then our next step is problems. We can have problem or problems. We're kind of, main goal is like we're going to design a problem that would take you 10 minutes to solve. Aim for like 20 minutes to do the quiz, but the goal would be like you're prepared, you're ready, you're just trying to demonstrate knowledge in this module. So what kind of problems would you use to like demonstrate? It can't be everything. It's not like you can't solve everything in 10 minutes. It's a whole, we spent weeks on this. I mean, maybe you could crank it out a little quicker now because you're so prepared, but something that kind of captures pieces or maybe overlapping concepts between the two. So what kind of problems should we work on? What do you want to use to demonstrate your knowledge of this module?
I would say probably like having like an example and then we call it free body diagram or something like that. Okay, yeah. Okay, that would be cool. Yeah, if we had like free body diagram and then like, okay, where is this thing accelerating? Because we did that, we tried that a few times. And I think that's one of a bird. Okay, I like that. What did you say then? That's a word pretty addressed. I would take it more upright. Well, yeah, but where is thrusting? What's it like? So I'm just thinking of the mass. Yeah, but like if you're talking about the body, I expect it from the shoulders. From the shoulders. Yeah. And well, I mean, when I see a bird, I'm thinking like upwards, like a drag force. Okay. Versus like the amount of force that the bird is actually like accelerating. Okay. Oh, okay. Like so like yeah. So they're like so like the drag is of everything and then there's just slightly less. Okay. Normal force, so that's how they increase. Okay. I was also thinking of like the vibrating also by that way there's just resistance that yeah. Yeah, like steady state would just be when the bird has its wings out. There's no thrust. stages of playing. Yeah. Playing games? Yeah. You're on the spot. Rocket ship all back to that day.
I'd say stuff similar to what we had before, kind of in parallel. I like the points and directional questions that teach you with coordinates and vectoring.
Okay.
And then if you want to do free body diagram, instead of Spider-Man, Green Goblin. And then maybe him on his thruster.
On his glider.
That way you can check his movements. And then the direction of motion one, I'm kind of still here and there on.
Okay.
Trying to think of which one I like Jimmy's.
Yeah. So like luge we had. Yeah, usually so with that one you have like two things I've been considering. How fast is it accelerating versus like what is the centrifugal acceleration? So those are like two components. Downward motion versus yeah, but somehow.
We did that before, so I can always like copy it.
Yeah. What would be
We get the boss, I know I'm failing one. It's like, yeah, either that one or the dad or his daughter fighting that. They were bad. It was. I did it right. I had to change the tree. And then they were like, oh, friction, you should be. I'm like, oh, well, that's so easy.
Yeah, some people are like, what's wrong with it?
No, because I knew it had to exist somehow to make it new friction. But I was making like new times four. Which I guess is just means.
Yeah.
Chris and Wise this one only work vertically. Okay, cool. Because somebody defined it to me that it worked on like moving towards that feels bad. The force, I was like, that seems dead long. It's called work.
But I still ended up with it.
No, because it's distance. No, I've got my answer. I wasn't waiting for you to finish your statement. I'm sorry, I got my answer. We're in the future now. No, that's what I'm saying. I was just like, why on earth would they call it? Why would earth would it only be vertical? That wouldn't make any sense. There's only working one possible direction. Screw the direction part. You're right. We have to rotate everything relative to this thing. It's like radius. They never taught us how to do, how to find a rating. Like we learned how to convert from radians to degrees, but they never taught us like how they interact with degrees. Not for mine. For you guys, yeah. For me, they were just like, here's a rating. It makes so much sense.
What if we do a limit? Doesn't it just work out to L'Hopital? That's what I was thinking. If you, yeah, sure. Unless you. Oh, yeah, the exam. All right. So one question came up of like. What is the acceleration as an unstoppable force meets an immovable object? No. So F equals ma. Everything's linear, right? Because no matter where the force is pushing, it's got to move in that direction or nothing, right? So then we can say F over A is, or sorry, F over M, my bad. And they're both, if they're both going to infinity, then isn't it just 0? Right? L'Hopital's rule, they both, it's either 0 or 1. That would be my thought. I don't know. Unstoppable force, immovable object. I think nothing happens. That's what I think. Nothing happens. Next existential question. Boom, nailed it. And then that's what I do. But you could always have a rebuttal. Then we had the idea of like, usually it's like a capsule, right? Coming back to Earth. And then we need so capsule coming back to Earth. What would free body diagram look like for that? For capsule, like a piece of a rocket coming back into Earth. Do you know why it gets so hot? You do? From terminal velocity? Terminal? Like friction, sorry. From pressure, yeah, there's some kind of, so, yeah, I guess depending on how we're talking, but it's that fluid mechanics, right? Like, when you move through a fluid, it takes work to get it out of the way, and so, yeah, at this point, to call it friction is not wrong, because there's definitely, like, the fluid that's against the ship wants to stay still, like there is like a boundary layer that wants to stick to the ship, but it's got to shear off of that. So moving that fluid, and we're actually, when you're re-entering, you're going way faster than terminal velocity. Terminal velocity is kind of like your steady state of like, that's how fast you fall when gravity equals drag. Here your speed is so much higher than that terminal velocity that you need to slow down. The only thing slowing you down is moving that air out of the way as quick as possible. So we could kind of say like, all right, well, this whole thing is just a drag and gravity problem, right? We got mg, and we got drag. It doesn't look that hard. It doesn't look as unsafe when we just have two friendly arrows like that. And then the question would just be like, all that work done by drag, it's all heating up your ship. It heats up the air around you a little bit, but for the most part, your ship is the thing getting hot. So it's that. And then what else? Did I see anything else so far? I'll check and see what else we have too. Yeah. Is this like, is the child ready for it, or is this
Never ready.
they're not trying to catch it in their mouth?
No.
No?
It's like the cat, you just throw a cat, the cat, like,
Yeah.
yeah.
Yeah. Okay.
A perfect example.
Yeah. Oh, that's right. And then, yeah. Go back to. I'm going to say they're ready for it. So a question, kind of like tossing kinematic problem, like what do we need to happen at the beginning so that someone can like either catch or impact can happen, that you can land a piece of cheese at the end of your trajectory. Here, what does free body diagram look like on that block of cheese though? Just gravity? Just mg? Yeah, maybe there's some drag, but probably not a huge amount. Force of the throw? Is that happening? When does force of the throw happen? Right at the beginning, right? So, and I think we talked about this a little bit when we were talking about differential equations. We can create an equation of like, all right, what's happening during the throwing versus what's happening after the throwing. So it would almost split it into like the throw portion and then flight. Kind of general, kind of dynamic sort of thinking about this is like, don't try to put everything into one free body diagram. Figure out where you can split it up. So you can go from, if you want to call it T0 is beginning of the throw, T1 is the end of the throw, then there's like some amount of time where you apply a force, and then some amount of time where there's no force applied. And that would be one way to think about it. And then we had, which I had forgotten about. And then it was purple. Green Goblin trying to outrun Spider-Man. Like, what are the forces on Green Goblin? This one, like gliders like this, and same thing with hoverboards. It's kind of a weird problem. Like the general problem is called an inverse pendulum, where the center of mass is above the thing that's supporting it. So like if all the Green Goblin did was just like, all right, let me light these rockets with no controls on it whatsoever, it would definitely flip upside down and like fly, like tumble away, send the Green Goblin flying. So you need some kind of feedback mechanism to make sure, like, as you tilt the thing forward, it moves forward. As you tilt it backwards, it moves, and side to side. Like, you need a feedback loop, which is kind of cool. So we could look at either the actual motion of the glider, or even like what are the forces that are there. Cool.
I meant to message you about that because I was like, Chris and I got it right. Chris submitted. Chris submitted. To be fair, yeah, we have business days. Wait, what did you know? Oh, she was gone. Okay, so just all Thursday and then all Friday.
So when is the show this on? I know more circle down and I understand how to do this. But every time I get like the angles right, I'm getting like okay, it's 45 in that world, but it's 90 in the real world. But then the quiz had it as 1.5 relative, so I was like, shit, man. I was like, what the half the real world? What is the question? Is half the real world? Yeah. 1 is 2. Okay. And then so to get the maximum, I rotated by 90. What would be 45? Oh yeah, because AC is real. That was it. That was it. The free body diagram stuff that I thought I understood like 10 stories and like, oh, I could go back to that. Integrating to matrices, that was annoying too. Okay. No, I mean for like the equation. No, not that. I'm talking about bringing back the combining IK and JK and stuff. I have to go back and understand that. It is, that part's easy. It's just iterating through it. I know there's like tricks that you can.
So, like, one thing that was cool that came up was like not just a problem, but also like conceptually, how do you explain the relation between position, velocity, acceleration? And like we talked about math relations, like what is the actual formula between them? So you could use that, or think about it like general, like what is velocity versus acceleration? The other one that, as I was walking around, it was kind of like two versions of similar things. One was like, let's make the surface rough. Let's say we've got like a box sliding. Kind of how far is this box going to slide along a surface? And we did that in how far will it go? Then there was another one that came up of a car driving up a hill. And this one I thought was interesting. If a car's driving up a hill, what's pushing it up the hill? Friction? Friction between tire and road? Yeah? Force of friction up the road? What do we think? Yeah. So rotating tire. So here's a question. Can you go up a hill without friction? Yeah. I mean, anyone who's tried to drive up an icy driveway knows it is not a fun experience because friction is your friend. Friction does help you up. This is actually kind of cool because that static friction is actually like keeping your road. The only thing you can depend on is the fact that your tire's not slipping. If it starts to slip, you actually lose all that torque that you're putting into your wheels. It's all gone. It's no longer accelerating you. So in terms of like external force, it's a static friction force driving you up the hill. And start, oh no, we only have 2 minutes left. Okay, so then we'd have like an mg, so we could figure out like maybe what's the max incline you could drive up or something like that. So let's go through. We had great, I like the way that you're like thinking about problems that we've done and this kind of thing. Who feels like ready for unstoppable force? This one's kind of weird. This one's like a tough one. Ready for L'Hopital's rule. Maybe? Ready? What about like looking at like flight? Either kinematic equation kind of flight, thumbs up or thumbs down, or falling, thumbs up, feels ready. Okay. I won't push you to the, I'm not going to have you like derive hyperbolic tangent equations for like what is velocity as a function of time, but maybe like here's current speed, what is force on it, something like that. What about glider? Yes or no? This one could be like we could end up, if you wanted, you end up with like a coupling, which is a little weird for free body diagram. We haven't really done that. All of our free body diagrams have been point mass. So this one might be a little strange. Maybe less. A little less. What about explaining relations between kinematic properties? A yes? Okay. Sliding box. Car on a hill, driving, medium, everybody's okay? Cool. And then this will, it says due tomorrow, but I'll push it off again because homework was due today. We just built the quiz, so you need some time to like digest it. I also need time to put it online, so it won't be due tomorrow, I'll push it off. Thanks so much. I'll catch you Wednesday.